Okay, folks. So we are ready. Uh, I hope people on Zoom can hear and see. Somebody confirm that you can see or and hear.
Yep, we can both see and hear.
Okay, great, excellent. Now you can mute. Okay, so the lecture we started with this little demo from Unitary of their latest humanoid. So those of you who are in class had the pleasure to watch it in 3D and or 4D, while the rest of you got the version on screen, which is fine. So what's the content of today's lectures? So the first lecture, which I always call 2A, the A lecture is the first hour, and this is going to be about robot kinematics and dynamics. The second lecture is going to be about human hands. And let's see how it goes in terms of whether I can actually manage to finish the first lecture in 1 hour. Now, what's the problem I'm trying to solve? Okay, so whenever we have a robot, like the humanoid we see, we have the following practical issue that we need to solve, which is that we have to deal with a whole lot of geometry to understand the kinematics and dynamics of the robot. So on this slide, what you see is the basic setup, and you'll understand it better once I explain it. So we have a robot here. So this is a robot with some degrees of freedom. And this is just an arm, robot arm. We can have humanoid, we can have hands, whatever. These are all kinematic mechanisms. And there's a coordinate system S, which is at the base of the robot. So think of it as a coordinate frame, which is fixed in the world. So it's at the base of the robot, or it could be in some corner of the room or whatever. Then we have a coordinate frame B, which you can think of as the body, the coordinate frame on the body. And this is related by a series of coordinate transformations. So we have a series of joints here because there's a series of linkages of the robot. And that's what we are trying to understand. Okay, so let me explain this better with the first the terminology. So the terminology is that we have a space frame S, which could be at the base of the robot. It could be a corner of the room. We have a body frame B, which is attached to some body of interest. So that's generically some frame which moves. And very often we might consider B to be the end effector. So the end effector of the robot may be where the frame B is. And all frames are right-handed. Okay, so this is hopefully stuff you remember from your physics and math classes. Okay, now there is a little bit of mathematical terminology here. And I'm going to tell you a little bit about this in the course of this lecture. What I'm going to do here is kind of this one lecture summary of what is normally taught in a few weeks in, for example, ECS 106, the undergraduate robotics class. And some of you know this material well, so you will either get bored or it'll be a useful revision. Some of you have never seen this before, in which case you'll at least know what's the right set of mathematical tools to look for solving this problem. You will not fully understand it from this lecture because it really is math which should be done by solving problems, and it takes a few weeks to do it properly. But I only can afford to do one lecture on this. Okay. Okay, and this is the big picture. At the end, hopefully you will remember this one thing, which is we find a way to characterize the kinematics of the robot through the product of exponentials. Okay, so this is what you see here. You see a whole bunch of e to the somethings. Okay, so there is m, which is the rest configuration. S1, S2, so on. These are what are called screw axes. So the S is for screw. Theta 1 is kind of that for example, the joint angle, something like that. Okay, and that is essentially telling us how the final frame, the frame of the body, is related to the original frame, the S frame. And this is the basic setup. So with this, we can do a bunch of different problems. People on the Zoom are going to miss this. Forward kinematics. Forward kinematics refers to just the geometry. Okay, what's the configuration of the B frame relative to the S frame corresponding to some set of joint angles? There is forward dynamics. And forward dynamics refers to sort of physics, Newtonian stuff, forces and torques. So there are forces and torques which are being applied by the robot, right? So there are motors at every joint which are applying torques, and this means that there is some force and torque at the end effector. So for example, if you want to pick up an object, you need to apply enough of a force to lift up that object, and so on, right? So that's the forward dynamics, which is what do I do on my robot? What joint angles do I have? What forces do I apply? Okay. And what's the consequence of that? And then there are inverse kinematics. Inverse dynamics. What do these refer to? What is inverse kinematics? I have a certain desired configuration that I want of the B frame. How do I achieve that? What joint angles do should I choose so that I get the desired configuration of the B frame? The same thing with respect to forces is the inverse dynamics problem. So we have a forward version of these problems. Kinematics concerned just with geometry, dynamics concerned with physics, and then there is the inverse version of the problem. And this is all very classical material. I mean, the basic laws of physics for this were all known by the 19th century. In the robotics community, when these manipulators started to be built, I mean, it was 50s and 60s and 70s and 80s, and I mean, it has all been worked out then. There have been different kinds of mathematical formalisms and notations that people have used. The mechanical engineers invented something called the Denavit-Hartenberg notation for specifying these coordinate frames across the different links. Starting from the 1980s, this product of exponentials notation, which was originally introduced by Roger Brockett. It comes from matrix exponentials, which are fairly commonly used in control theory. That has become popular. And at Berkeley, we teach, even our undergrads have to learn this. So even the undergraduate graphics class, vision class, graduate vision class, graduate robotics, everywhere we teach people products of exponentials. So you may as well get with the program. Okay. Okay. Next, I want to point out how the practical sort of computer science aspects of it. Every robot is described using this URDF, okay, Universal Robot Description Format. And this specifies the geometry of the robot. And this is done. And in addition, we also specify the inertial properties, like, for example, mass. So all the lengths, what are their lengths, what are the angles, what are their masses, all of that. There's a certain way of specifying this as an XML file. And then we can work with that. So simulators know what to do. Okay, so I'm not going to go into how the specification of a URDF. It's boring, but it's all worked out. What I want to do is to talk about this product of exponentials. I mean, that's the big idea that we want you to So I'm going to talk about this essentially first in a purely mathematical way, and then later on we'll see how this applies to robots. But it's really all about understanding rigid body motions. What do I mean by a rigid body motion? A rigid body motion is where the body is rigid. What does rigid mean? If I take 2 points on the body, the distance between them does not change. That's the definition of rigidity. If something is elastic or stretching, then the distance between a pair of points on the body does not remain the same. Okay, so we are concerned with rigid body movements. Rigid body motions, there are a number of names for this in different communities. Sometimes these are called Euclidean transformations. Okay, because Euclidean geometry is all about what properties are preserved under rigid body motions. You can consider a triangle and you have the notion of two triangles being congruent. What is that? That's really saying that if you do a rigid body motion and they are the same, then the properties are the same. Okay, so Euclidean transformation is one term. Another term is isometry. So this is a term used by mathematicians. What does isometry mean? Iso means equal. Metry is about distance. So that means distances are preserved, which is again the definition of rigid body motion. And I've stated this mathematically, which is you have some points A and B. You apply this transformation psi of A, psi of B. After the transformation, I can find the distance between them. That is psi A minus psi B, right? That's that norm of psi A minus psi B. That's the distance between the transformed versions of A and the transformed version of B. And that should be same as the original distance. What's the original distance? That's on the right-hand side. A and B, the distance between them. So you take A minus B and you find the length of that vector. So that's the definition of a rigid body motion or a Euclidean transformation or isometry. All of these terms we use equivalently. Okay, what are examples? Essentially, the examples are going to turn out to be rotations and translations. Translation is an isometry, is a trivial statement. I've got this one-line proof, right? That if I have some point A, the translation means that it's shifted by this vector t. And so A goes to t plus A, B goes to t plus B. You find the difference. You find the length of that. It's the same as that of A minus B. So translation is trivially an isometry or a rigid body motion or a Euclidean transformation. This is one example. There is another one, which is rotation. But rotations actually belong to a family of transformations called orthogonal transformations. Orthogonal transformations essentially fall into two families, rotations and reflections. Rotations have determinant +1, reflections have determinant -1. We are going to be concerned about rotations. So these are determinant +1. So any rigid body motion can be expressed as an orthogonal transformation followed by a translation. Okay, I just have to define orthogonal transformation here, but think of it as a rotation or a reflection. And after a while, I'll throw away reflections and only be concerned with rotations. And in linear algebra, how we express this is that there's a matrix A, okay? And this is a so-called orthogonal matrix if it corresponds to an orthogonal transformation. And then the translation part is shown by this plus t vector. Okay, what's the definition of an orthogonal matrix? Orthogonal matrix is defined as a matrix where every column is of length 1 and any two columns are mutually perpendicular. And we can do this for 2 dimensions, we can do this for 3 dimensions, we can do this for 17 dimensions. In 2 dimensions, essentially the fact that each column is of length 1 means that you can characterize it as cosine theta, sine theta. The second column has to be perpendicular to the first one. So therefore, you get that it must be minus sine theta cosine theta. So there are two versions of this, and those are shown in this this matrix here. Let me see if my mouse will do. So there's a version here which has determinant +1, and there's a version here which is determinant -1. The determinant +1 corresponds to a rotation. Determinant -1 is a reflection. In future, we'll care only about rotations. And this is the matrix. And another way to understand what this matrix does is what happens when you apply this matrix to the vector 1, 0. When you apply this matrix to the vector 1, 0, what's going to happen is that essentially that will select the first column. So you get cosine theta, sine theta. And if you apply this matrix to the vector 0, 1, you'll get the second column, minus sine theta, cosine theta. So this corresponds to rotation of by theta. Again, I would do this with lots of examples if this was the first time you were seeing these ideas, but I hope this is not the first time. Okay, now we go to 3 dimensions. So in 3 dimensions, we are going to have 3 by 3 matrices. These are 3 by 3 orthogonal matrices. So what's the definition? Each column is of length 1. Any 2 columns are perpendicular to each other. That means that the dot product of any 2 columns is 0. So that's a definition of a orthogonal matrix. So this essentially gives you 6 constraints. So even though this matrix pretends that it has 9 numbers, it's not in fact 9 independent numbers. It's actually only 3 degrees of freedom because of the 6 constraints. Okay. And again, the model, there's the rotation version and the reflection version, which corresponds to whether the determinant is +1 or -1. We care only about determinant of +1. And here are some, let's take some baby examples to get a clear intuition. Okay, the easiest one, which is at the top. What is this? So this is, if you confine your attention to the first 2 dimensions, the x and y, then what do you get? You get a cosine theta minus sine theta, cosine theta. What does that remind you of? That's basically your planar rotation by theta, right? Okay, that's just your standard rotation in the plane. And what's happening on the z-axis? Nothing. That's where that identity, you just have that 1 in the 3, 3 position. So this is rotation about the z-axis. So this is just the natural generalization of rotation in the plane. I added the z dimension, but I chose to do nothing there. So that's my matrix. So that's the matrix for rotation by theta about the z-axis. And similarly, you can construct matrices for rotations about the x-axis by theta, and similarly for y-axis, and so on and so forth. Okay, so this is just simple intuition. How do we parameterize rotations in 3D? Okay, there are like a zillion different ways. The original version was Euler angles, because Euler was the mathematician who first sort of understood rotations properly. And so there's Euler angles. There's the one that I like, the most intuitive way to think about rotations to me is there is an axis of rotation, and then there is some amount of rotation. Okay, how do you specify an axis of rotation? How many degrees of freedom does the axis have? An axis is it's in 3-dimensional space. So you might think it's 3 dimensions, but no, you only care about its direction. So you can think of it as a unit vector. So therefore, the axis is specified by 2 numbers, because it's a unit vector corresponding to the direction of the axis. And then there is an amount of rotation, 30 degrees, 50 degrees, whatever. So therefore, there are 3 numbers, 2 to specify the axis and 1 to specify the amount of rotation. Then there is a technique called quaternions, which is the generalization of complex numbers. So in 2 dimensions, multiplying by if you think of your point as a complex number, then multiplying by complex numbers of modulus 1 is equivalent to doing a rotation. But in our setting, we are concerned with three-dimensional space. So the generalization of complex numbers to three-dimensional space is this concept of quaternions, which was invented by this Irish mathematician called Hamilton. And the story is he was taking a walk, and then he had this brilliant idea, and he sort of marked it on the stone on a bridge that he was walking on. I don't know whether it's true or not. When I go to Dublin, I will try to find that bridge. That's the claim. And of course, the 3x3 matrix is a representation of rotation. And for different purposes, we use different representations. Often for a neural network, you often want redundancy. So actually, a 3x3 matrix is a pretty good representation. But if you want to do smooth interpolation, sometimes people like quaternions for that. Anyway, this is not the time I'll get into that in detail, but just be aware that there are many ways of representing rotations. Okay, next. Now I'm starting to get to stuff which is going to take us on this path of exponentials of something. So this is the idea of cross product. So vector cross product is something you have learned in physics, but and that's the top notation. So I'm using this notation here. Okay, it's the same as this vector cross product. Okay, I mean, often in physics, you might have used this cross, but I'm using this symbol. That's just a variation. And the definition of cross product, okay, you've seen that before. And what we can do is it's a linear operation, doing a cross product. So therefore, it should be expressible by some kind of matrix multiplication. And that matrix is what is shown in the middle here. So this matrix A hat, it has the property that when you multiply this matrix A hat with the vector B, so consider what's happening here. This matrix A hat is multiplying a vector B. I get by just this matrix multiplication. So this is my matrix here. I multiply this with this vector B1, B2, B3, and I'm going to get this result. So 3x3 matrix multiplies a column vector. You're going to get a 3. You're going to get a 3x1 column vector, and that's the column vector here. And this column vector looks the same. In fact, it is exactly the same as that column vector at the top corresponding to a cross product. So what this says is, you learned about cross products in high school or wherever, and equivalent way of doing cross products is take the three entries of this vector A1, A2, A3, put them together in this matrix in this specific way, and then using that matrix for multiplication gives you the same result as taking the vector cross product. Is this clear? Any question on this? So please interrupt wherever you have questions. Okay, and this matrix is a particular kind of matrix. What's the property of this matrix? It has zeros on the diagonal. It has some entries above the diagonal and some entries below the diagonal, but they are negatives of each other. So this is a so-called skew symmetric matrix. Skew symmetric matrix, which means that A transpose equals minus A. That's the definition of a skew symmetric matrix. Okay. So what we have done is we've taken a vector, converted it into a skew symmetric matrix, and that skew symmetric matrix, if you multiply that with the B, a vector B, you get the cross product of A and B. Okay, so far so good. Now we start to move to more interesting stuff, which is basically I'm going to show that the exponential of a skew symmetric matrix gives you a rotation matrix, and that this is the right way to think about rotations. They are exponentials of skew symmetric matrices. So we'll do that first. And then there is a more general version of this, which is the exponential of a twist gives you a general Euclidean transformation, which means a rotation plus translation. I'll give you the intuition reasonably clearly for rotations, and for the twist story, I'll be more just waving my hands and not go into complete details. But hopefully you get the idea. Okay, so let's take this step by step. So first of all, how do we think of a rotating body? So the equation of motion of a point on a rotating body. So the point is Q. Okay, that's the vector coordinates of the point Q. And Q dot is, how is that changing in time? So it's dq upon dt. So Q dot of t is omega cross product with Q. Okay, so this is again from your physics of angular velocities, you should remember this, right? Here omega is a vector, and this is the angular velocity vector. And the angular velocity vector has a direction which corresponds to the axis of rotation, and its magnitude tells you the speed of rotation in terms of radians per second or something like that. So omega is a vector, its direction is the axis of rotation, its magnitude is the rate of rotation, radians per second. Okay, so Q dot is omega cross Q of t. And in the last slide, we learned how we can do cross products. We can do cross products by multiplying by certain matrices. And it is the 3 by 3 skew symmetric matrix. So that's what I've done. So this omega hat here is the matrix. So omega was a vector, but omega hat is a 3 by 3 matrix. And now this equation Q dot equals omega hat Q. This guy is a 3 by 3 matrix. And this is a 3 by 1 vector. And this is also a 3 by 1 vector. Okay. So now it's a vector matrix product, which tells us what is Q dot. Q dot is the change. Okay. So far, so good. Okay. We've just taken the standard physics stuff. We've converted it into a notation where vector cross products have been replaced by matrix multiplication with skew symmetric matrices. But this is actually a differential equation, because this Q dot is a function of time and this Q is a function of time. And now we want to solve this differential equation. Okay? Right? Okay. Now, how I have to solve this equation, and it turns out that let's think of something we know how to solve. X dot equals AX. Right? This is the simplest differential equation that you can learn. And the solution, what's the solution to this differential equation? The solution to this differential equation is x of t is e to the at x of 0.
Jitendra?
Yes?
Sorry, it's Shirley. Can you turn off the blur on your camera?
I can turn off the blur on my camera. I don't know how to do that.
If you go to the video on
Yes.
your Zoom.
Yeah, I've now turned it off.
Just turn off. You have it clicked, blur my background.
Okay, can you just come here and do this for me?
Thank you.
Where's your Zoom? Oh, here. There you go. But yeah, so then they wanted to see the whiteboard, so now they can see it.
Oh, okay. They want to see the whiteboard. Okay.
Yeah, let's just
Thank you
close
so much.
Okay, now just close whatever. Yeah, I mean, there isn't much substantial on the whiteboard, just to know, because it's everything is there on the slides, really. So just in case you miss something, you haven't missed too much. Okay. Is that hopefully that's working? Okay, bet. So x of t equals e to the at x of 0. Okay, we can verify that. If you take the derivative of this, what are you going to get? The derivative is a times e to the at, right? And you can see that that satisfies the differential equation. Okay. And there's an initial condition that you always need, and the initial condition is that x of 0 is given. So this x of t equals x of 0 times e to the exponential of at is the standard thing which you learned in your very first differential equation class. So what do we have here? So what we have is now it's something which looks similar, except that we don't have these scalars. What we have are vectors and matrices. And it turns out that actually the whole story still works. Okay. So what we have here is this expression q of t equals e to the omega hat t q of 0. And this e to the omega hat t, what does that mean, right? Where omega hat is a 3x3 matrix. It's a Taylor series expansion of E, but it is the omega hat is the funny thing here compared to the A, which is a scalar. Omega hat here is a matrix. So now you remember the Taylor series expansion of just e to the t, right? You know what that is, right? It is the e to the omega hat t, where omega hat is a matrix, is exactly like that, but we are now dealing with matrices. So you get I. What is I? I is the identity matrix, the 3x3 identity matrix. What is this the equivalent of for when we had scalars? The number 1. Omega hat t. Omega hat is a 3x3 matrix. Previously, you would have just had the number a times t, and so on. So the t is a scalar, as that t is standing for time, but the omega hats here are 3x3 matrices. So you have omega hat t squared, omega hat t cubed. And how do you what does it mean to have a matrix squared, matrix cubed? You just multiply the matrix by itself. Okay. So I've skipped some details here. I mean, a mathematician would probably put me against the wall and shoot me because all the rigor is missing, but it all works out. Okay, so the mathematical thought police can be satisfied. Okay. Okay, and then there is some very cool stuff which happens, that if you take this, so you've got this infinite series involving all these powers of this matrix omega hat. It turns out that these powers are not, they don't give you different matrices after they start to repeat. And if you put together all the odd terms and you put together all the even terms, you essentially get this, this Taylor series, this infinite series can in fact be summarized in 3 terms. The identity plus sine phi times this S hat matrix plus 1 minus cosine phi times this S hat squared, which is basically a 3x3 matrix. And this is beautiful. This formula is called Rodriguez formula. And it can be derived by purely geometric methods and not requiring all this exponentials mumbo jumbo. But once you know the exponential mumbo jumbo, this is a super clean and simple way of doing this. Okay. Okay. So now you've understood. So let's go up and try to look at the big picture. So the S hat is characterizing an infinitesimal rotation, a very small amount of rotation. Now you keep doing this rotation for a finite amount of time t, and what you get is a full rotation matrix R. And that full rotation matrix R has to be related to the axis of rotation and the rate of rotation. So the axis of rotation is captured by this S hat matrix. The amount of rotation is captured by phi, which is just your angular velocity in radians per second. If your velocity is 0.2 radians per second, and then if I run it for 5 seconds, what do I get? 1 radian worth of angle change. So this is rotation by 1 radian. Let me pause here to see if anyone has any questions. Okay. I know I'm going through this very fast. I mean, because I'm hoping that most of you have already seen this. But for people who are seeing it for the first time, the magic that you are supposed to, go all thrilled about is that we had an infinitesimal amount of rotation which we capture by the axis of rotation and rate of rotation. That's given by this S hat. And then we rotate by an amount of time t, and now we get a full rotation matrix. And that rotation matrix is the exponential of phi S hat. And in fact, there is a fairly nice compact formula for it. Okay, so this is, and okay. Any questions on this? Okay, let me actually take a poll here. How many people here have seen this before? Okay, so 50-50, which is fine. Okay, that's what I expected. Now I will run through some basic facts about isometries, which are kind of intuitive, which is the composition of two isometries is an isometry. So this is kind of straightforward, right? You just you do some multiplication, and so there's a rotation matrix A and then a translation T, and you have two of these. So one is psi1, one is psi2. You compose them together, you'll get another isometry. I'm using the term isometry interchangeably with Euclidean motion, or it's like a rigid body movement. They're all the same. Isometries every isometry has an inverse, meaning that there is an A and a T, and then it does something, and there is the inverse of that, meaning that if you compose so you have a isometry A, and then there is some isometry B such that B composed with A is the identity. So you can think about this, right? If there's a rotation, then you just do the opposite. Okay, if there's a rotation and translation, it turns out there is some rotation and translation which cancels it. And there's an identity element, which is, what's the identity element for isometries? The rotation matrix should be a identity matrix. The translation vector should be a zero vector. Okay, so that's the identity corresponding to this. Okay, what I'm doing here is I told you the story for rotations, right? I said rotations are easy to think about. Exponentials of skew symmetric matrices. That's what rotations are. Now I'm getting you ready for the general case. And the general case is that there will be a rotation and a translation. Okay. And first, I'll have to figure out how to express that in matrix form, and then how to convert that to exponential of something. That's what I'm leading up to. So, first, another bit of preparation, homogeneous coordinates. Homogeneous coordinates are that when you are in any space, these require having an extra coordinate. So if you are in one-dimensional space, normally you use one number. In homogeneous coordinates, you use two numbers. When you are in two-dimensional space, normally you need two numbers. But in homogeneous coordinates, you need three numbers, and so on. So basically, in any in n-dimensional space, we need n plus 1 numbers if you use homogeneous coordinates. Okay, you might be wondering why do we want to do this? first of all, this adds redundancy. So how do we resolve the redundancy? So the redundancy is resolved by this characterization, which is that if you have a vector of coordinates, right, then any scalar multiple with a non-zero value of that scalar corresponds to the same point. So this x1, x2, so on up to xn vector corresponds to the same point as when you take this vector and you have every component multiplied by lambda, which is non-zero. So basically, we added an extra degree of freedom and then we took away the degree of freedom. It sounds stupid. It actually, where it delivers value for you is in dealing with what are called points at infinity. And there's again, a long story here, which is that, for example, perspective transformation, which we study in computer vision, these are a subset of what are called projective transformations. And with perspective transformations, you have the phenomena that parallel lines can meet at a point. Okay, but that, how do you almost nodded, but that's not true, right? Lines which are not parallel intersect at a point, but parallel lines don't meet at a point. So we have to make a story. The story is that the parallel lines meet at a point at infinity. And how do you characterize a point at infinity? Okay, in regular Euclidean coordinates, the Cartesian coordinates that you learned from, again, in your high school, those don't deal with that. But once you have homogeneous coordinates, then you can allow for points at infinity if you make the last component 0, for example. But anyway, I won't get into that because this is not a computer vision class. I don't have to teach you about perspective projection and projective transformation, but this is kind of a motivation. But the short story here is we go to one higher dimensional representation, but then we remove that degree of freedom by saying that scalar multiples correspond to the same point. Again, look it up on Wikipedia if you have never seen homogeneous coordinates before. Okay, this now helps us because this now enables us to represent general Euclidean motions by a matrix. So this is the representation that I'm going to talk about. So we are now dealing with isometries in three-dimensional space. So these consist of a rotation followed by a translation. So in this 4x4 matrix, the first 3 rows and first 3 columns, what do they look like? Since they have the letter R, what do you think they correspond to? Some rotation, right? Good choice. Yes, good guess. So this R11, R12, R13, that 3x3 submatrix corresponds to the rotation part. P1, P2, P3, this corresponds to the translation part. Okay. And you can see that this is a 4x4 matrix, even though we are dealing with transformations which are in 3-dimensional space. Well, what does this 4x4 matrix want on its right-hand side? A 4x1 vector. How do I get a 4x1 vector when you have points in the 3-dimensional space? Homogeneous coordinates, right? So the homogeneous coordinates of a point in 3 dimensions are going to be a 4 vector. And the trivial way of making homogeneous coordinates is as follows. So suppose I don't know, just name me some vector in 3-dimensional space. 2, -3, 7. This is a vector in R3. Okay? I want to express this in projective 3-dimensional space. What do? I need to make it a 4 vector. It's 2, -3, 7, 1. Just add a 1. Okay. So this is a trivial way by which we can convert any of my usual 3-dimensional points in a 3-dimensional space into a 4 vector, which is what we'll need in this setup. So this gives you no additional value. The additional value comes in when we are dealing with points at infinity. So points at infinity, you can have, instead of that 1, you can have a 0, and you can essentially consider points at infinity, but we won't deal with that here. Okay, and this so now there's a little exercise which I won't take you through, which is that if I take any point, let's call this, I don't know, let's call this x1, x2, x3, 1. That's my point, x1, x2, x3 in three-dimensional space, and I'm converting it to by adding 1 as the last component, right? So now it's a point in, I'm using the same, it's the same point, but expressed in homogeneous coordinates. Now I can multiply that 4x4 matrix that we have in the slide times this vector x1, x2, x3, 1. Okay, do the algebra, and you will find that this will essentially turn out to be equivalent of the rotational matrix R applied to x1, x2, x3, plus the translation vector P1, P2, P3. So this is 4x4 matrix is honest to God representation of a rotation followed by translation. And this is kind of tricky to do because we love linear transformations. We love matrices. But why can't I do a rotation and translation as a straightforward linear transformation? Rotation is the linear transformation, but translation is not. See, if you just think of translation, we all think linear transformations are simple and easy, and translation is simple as easy, so therefore translation must be a linear transformation. No, that's not true. Translation is not a linear transformation, right? Just think about additivity. If you have a point A, it becomes A plus T. If you have a point B, it becomes B plus T. The sum of A plus B, it becomes A plus B plus T, whereas if you had linearity, it would be A plus B plus 2T. So translation is not a linear transformation, okay? So we have to go through some mumbo jumbo to make it into a linear transformation. And it turns out that going to homogeneous coordinates enables you to do that. And in this setup with this 4x4 matrix, you have both a rotation and a translation, which are incorporated nicely. Okay. Then this terminology SE3, special Euclidean group SE3. So the 3 here stands for, okay, let's just unpack these representation. What is the 3? The 3 is because it's 3 dimensions. YE, it's in honor of Euclid. Euclidean movements are rigid body motions. What is S? S is special. Can somebody guess why? What is the S for? The S is because we want to remind you that the determinant is +1. Okay. So it's a determinant +1 setup. So, okay. So SE3, and so what is SE of 2? It's a 2-dimensional Euclidean movements. How many degrees of freedom are there in a 2-dimensional, in the 2-dimensional version, SE2? Somebody? So it's 3 degrees of freedom because the rotation part has 1 degree of freedom and the translation part has 2 degrees of freedom. So that's a total of 3. When we go to SE3, 3-dimensional space, then how many degrees of freedom do you expect? 6. 3 for the rotation part, and then 3 for the translation part. The rotation part, it looks like it has more, there are more numbers there. There are 9 numbers here, but once you consider the constraints of orthogonality, it reduces to 3. So this is a 4x4 matrix, but how many degrees of freedom does it have? 6. Okay. Now I want you to start to think of the analogy with the case of pure rotations. So with pure rotations, what did we get? With pure rotations, we had a 3x3 matrix of rotations, and this was the exponential of a skew symmetric matrix. This matrix, this 4x4 matrix, we want to think of it as an exponential of something, right? That exponential of something, what are the degrees of freedom of that something? It should be 6, right? There must be 3 corresponding to the rotation part and 3 corresponding to the translation part. So this is what we are going to do some mathematical mumbo jumbo, but at the end of the day, you want to not lose sight of what it must land up with. So that there is a 6-dimensional entity which corresponds to an infinitesimal movement, a very, very small movement. And we call that a twist. Twist. So twist is going to be a 6 vector. And this will correspond to 3 for rotation and 3 for translation. And there will be some black magic by which we take an exponential of this twist, and we are going to get a complete Euclidean movement, a rotation and a translation. Okay, does that make sense? Because I'll get into stuff now which will go fast and will probably not be clear, but at least this notion you can hang on to, because it's a proper generalization of what the story was for rotations and skew symmetric matrices. Okay, let me just power through for a little bit and then I'll give you a break. So one is this 3-dimensional isometries in 3-dimensional space. They constitute a group, which means that there is an identity. You can compose them together. There is an inverse. So this slide writes down what is the inverse, and you can verify that, right? Because you can take some point x, give it a displacement rp, and then give it the inverse displacement, and you should go back to x. Yeah, which is why we can do all this exponential story. Okay, and now we have, and by the way, all this stuff here, I'm stealing slides from this Lynch and Park book, which you can, I think this guy has they have lectures on YouTube which you can watch. There's this book you can buy. There's also the book from my colleague Shankar Shastri, which has all this and more. So either of these textbooks cover this in great detail. And if you really want to understand it, read it from those books. I'm giving you the cartoon version of this whole story. The real thing, you should read those books. Or take 106. I'm curious, how many people here have done 106? Okay. Or the moral equivalent of that in other universities. I don't know whether everybody does exponentials of twists or not. Okay. Okay, I think this is time for a break. Okay. So my lecture 2A is going to go on for longer. We will resume in 10 minutes. But this class, I rose of good old mathematics. Okay. There is this slide which I think I'm not going to spend too much time over, because it's just telling you that what displacements or isometries are used for. You can use them to talk about the relationship between one coordinate frame and another. You can change reference frames. You can think of this as an operator that you apply on a vector and you get a new vector. I think okay, wait. Okay, yes, now we get into what is called screw theory. this is very cool. This is one of the elegant results of this area, which goes back to the 19th century, and I think I'm going to do this because it's just fun. Okay, it's like sometimes you have to exercise your brain about. And this one, okay, first let me explain it a little bit for the people in Zoom land, and then I'm going to do the rest on the board. So it turns out that every rigid body motion, so a rigid body motion in three-dimensional space, that means that there is a rotation followed by translation, right? This is equivalent to what is called a screw motion. What do I mean by a screw motion? Screw motion means the following. There is some line in space. Okay, this line is called the screw axis. And what the motion is equivalent to is moving, rotating, and moving in the axis of the screw. So what happens with a screw, right? When you screw in something, I mean, there's a picture here of a screw. What happens is that it moves along the axis of the screw. There is a translational movement along the axis of the screw, and there is a rotational movement, right, around the axis of the screw. Translation along the axis and then rotation around the axis. Both happen. And then a screw has what's called a pitch. The pitch of a screw means how much in one rotation, 2 pi rotation, how much does the screw move in terms of actual position of the tip of the screw. So you rotate by 2 pi, then the screw moves by a certain distance in space. That is called the pitch of the screw. So the pitch of the screw refers to how much does the screw move in. So you're screwing in something into a piece of wood. How much does the tip of the screw move in for one full rotation of the screw? There's a term for this. It's called the pitch of the screw. So it all has to do with the threads of the screw. You can have the threads very closely spaced, in which case the pitch will be small, or the threads can be spaced further apart, in which case the pitch is long. So you understood the concept of a screw motion, right? The magical result is the following. A general Euclidean movement in 3D space, which is some rotation followed by translation, is equivalent to some movement along a screw axis. Okay. So first of all, so this is not obvious. It should not be obvious. If you think it's obvious, that means you haven't got it. Okay. It's not obvious. But first, let's do the degree of freedom counting. How can you, so the axis of the screw, okay, there's a line around which this screw movement is happening. How many degrees of freedom are there for a line in three-dimensional space? Okay. How many degrees of freedom are there for a line in three-dimensional space? Okay, let's do the baby version. Okay, I really want you to think, because otherwise that means that if nobody is, otherwise I would have to assume that everyone is asleep. Okay, let's start with the baby version. A line in two-dimensional space. How many degrees of freedom does a line in two-dimensional space have? No, 2, because there is the slope of the line, and then you can shift the line. So there's 2 degrees of freedom for a line in two-dimensional space. In three-dimensional space, how many degrees of freedom does a line have? Okay, so it should be more than 2, right? Obviously. Okay. Okay, let's take a vote. Let's see if since we live in a democracy, I want to prove that democracy isn't necessarily the best form of government. So therefore, let me count how many people think that. So everybody think, okay, I should do the active learning thing. You are allowed to talk to your neighbor and then discuss for like 2 minutes. Okay. Okay, and then I'm going to ask you to vote 3, 4, or 5. Okay. Okay. Okay, so now let's see if democracy works. How many people think that a line in R3 has 3 degrees of freedom? How many people think that a line in R3 has 4 degrees of freedom? How many people think that a line in R3 has 5 degrees of freedom? Okay, so 4 and 5 are kind of close. How many people think that a line in R3 has 6 degrees of freedom? Nobody. Okay, so you are off by 1. So it's 4 and 5, right? No votes for 3, no votes for. So that's good. Now it's 4 or 5. I think I see that maybe slightly more for 4. So maybe I do have increased faith in democracy. Okay. So let's think about it. Okay. How do I think of a line in space? So a line in space has a direction, right? So therefore, a direction, so that means 2 degrees of freedom, right? Because it's a direction can be specified by a unit vector, right? So that's 2. And then you can move the line about in space, right? So you might think that that is 3 degrees of freedom. But no, because if you slide the line up and down, that's not changing the line. So therefore, there is only 2 degrees of freedom. So therefore, there are a total of 4 degrees of freedom. So lines have 4 degrees of freedom, and there is a way to characterize them called Plucker coordinates, P-L-U-C-K-E-R. And once upon a time, everybody in computer vision used to know these things, but sadly, in the era of deep learning, people have forgotten all this. Okay, so the answer is 4. Okay, and I'll give you another intuitive way to think about it. Okay, this is the very easy answer. So construct 2 planes in space. Okay, so 2 infinite planes in space. Then this line must intersect these planes in space. 2 points on the top plane, 2 points on the bottom plane, therefore there are 4 degrees of freedom. Right? Okay, so it answer is 4. Okay. Now I want to say, but now the number of degrees of freedom with this screw motion. There is 1 degree of freedom which corresponds to the pitch of the screw, because you can have screws of different pitch, how tightly they are wound up. So 4 degrees of freedom corresponding to where you put the screw axis in space, 1 degree of freedom corresponding to the pitch of the screw. So that makes it 5. And then there is how much do you turn the screw? So that makes it 6. So a screw motion has 6 degrees of freedom, 4 corresponding to where you situate the screw as a line, 1 corresponding to the pitch of the screw, and 1 is the amount of screwing that you do. 6. So at least there is a sanity check that rotations and translations add up. I mean, those must have 6 degrees of freedom. This is a way to specify 6 degrees of freedom. But now I want to do the if and only if part. Any rotation and translation is equivalent to some screw, right? So this is not proved, but at least we did a sanity check. If the degrees of freedom are different, then we know that we were going to be wrong. Okay, so let me do that. But again, as I said, this is not really necessary for this class, but I'm having fun, so I'll continue. Okay, now let's do the 2D version of this problem. Okay, so I'm using that to build up notation, intuition for this. So in 2D, you can have a translation and a rotation, right? So there is a rotation about, say, the origin. So imagine that we have So in 2D, so now I'm going to do the 2D case. So in 2D, we can do, there is some origin, let's call this 0, 0, and there is some rotation by theta, and then there's a translation, right? So it has 3 degrees of freedom in the 2D case, right? Okay. Now I am going to argue with you that except in one degenerate case, this rotation followed by a translation can be converted to just a rotation about some new point. So there is some rotation by theta, and then there is a translation by some amount. Okay, so this has 3 degrees of freedom. This is equivalent to a new rotation, and that's it. That takes care of both the rotation and the translation part. Okay, you can work it out with math, but let me give you an intuition. So let's see how good I can convey that intuition. So suppose there is some object here, right? Can people see this? Okay, so there is this object, right? What I'm going to do is I'm going to rotate it by 90 degrees and I'm going to translate it. So what did I do? I took this object, and let me mark this point A so you have some sense. So I took this ellipsoid, I rotated it by 90 degrees, and I moved it kind of diagonally, right? And I'm using this as just a proxy for you, but in general, it should be some arbitrary rotation and some arbitrary translation. This whole thing is equivalent to there being some center around here and then doing just a rotation. So you can, there is some other point about which you can do this rotation and it'll work out. And now the degrees of freedom, what are the degrees of freedom? That location of that point, so that's 2'd off. And then there's the amount of rotation, that's the 3rd degree of freedom. Okay, now this is, I can leave this as a little exercise for the reader, but the way I'll give you a hint to how to solve it. There is what is called the pole of a rigid displacement. The pole is defined as the point which is left invariant by the movement. So if there is some point P, and then I apply this transformation, which is Rp plus T, okay? And if Rp plus T is the same as P, Rp plus T equals P, this is the condition for P being a pole. And can you find a point like this? Okay, you can just do the math. It's I minus R. If I move this R there, I minus R P equals T, which means that P equals I minus R inverse T. So there is a point. I mean, so there's special cases when there is no rotation. If you do pure translation, then there is no pole. Or actually, there's a pole at infinity. But if you have some rotation and some translation, there is a point I minus R inverse T, which in fact does not move as a result of the Euclidean displacement. It turns out whenever you have a rotation, if you have a pure rotation, is there a pole? Yes, the center of rotation is that pole. So therefore, what you do is you can take, if I give you a rotation and a translation, you compute the pole, put the center of rotation there, and then it'll all work out. You can do the math. I mean, I leave this as an exercise to the gentle reader. Okay. So in 2D, we can prove that a rotation followed by a translation is equivalent to a rotation about some other point. And it's actually rotation by the same amount. So if it was 45 degrees, it's 45 degrees. Okay. Now let's take this idea and apply it in three-dimensional space. And now I'm going to do a bit of hand waving. So it actually turns out that this applies, and there are people called Charles. This is obviously a French name, and there's some Italian fellow called Mozzi. And these people, they kind of independently discovered this idea that in 3 dimensions, you have this idea of a screw axis, where that means that a rotation and a translation together can be converted into this screw movement. Okay, I'm not going to prove this, and I'll wave my hands, and so but half the idea should go through. So think of the translation with respect to the screw axis. You can think of the translation having a component which is in the direction of the screw axis, and the translation has a component which is orthogonal to the screw axis. Okay, the translation which is in the direction of the screw axis is easy to consider, right? Because you can always do that, right? Use the screw. Translation orthogonal to the screw axis is essentially a translation in the plane orthogonal to the screw axis. And in that plane, you can basically think of it as there's a translation and a rotation, right, about that axis. So it's basically back to the 2-dimensional story. And a rotation and a translation, I can compress this to an equivalent rotation by just shifting the axis of rotation. So the axis of rotation here is the axis of the screw. Okay, so slightly hand wavy, but the basic argument is that in 3-dimensional space, we are building on the proof for 2D that I did earlier. We can build on that proof, and then the 3-dimensional translation is broken up into 2 components, one along the screw axis, one orthogonal in the plane orthogonal to the screw axis. The plane in the plane orthogonal to the screw axis, you combine it with the rotation by just shifting the axis of the screw. So it all works out, and don't insist on rigor because I'm just waving my hands. You can see me waving my hands. Okay. Okay, so now, I need to get to my lecture 2B. Okay, so what's the point? Anyway, I find when I learned this fact, like somewhere when I was an undergraduate, I found this really cool because both these facts are kind of counterintuitive. They're very simple, but you can explain them to a high school kid. I think that is what is pretty about good ideas in mathematics, is that they are counterintuitive, and yet you can, once you get it, right? Okay, so now I'm basically doing the obvious stuff. So twist is a mathematical term here. So twist here corresponds to the infinitesimal part of a Euclidean displacement. So it's like a angular velocity part, which is this omega a, and then the linear velocity part, which is VA. Okay, so far so good. So the twist is a 6-dimensional vector. Okay, this just ignored because this is getting into all this, the mathematical theory of how you transform a twist vector in one frame to another frame. Okay, you have to use something called an adjoint. We are not going to get into all this. If you want to understand all this, take 106. Okay, and then you can represent a twist by matrix. This part is kind of intuitive, so I'm now just hand waving my way through. This part is intuitive because what is this? This is a 4x4 matrix. There is a top left part which corresponds to the rotation part, and what is that going to be? It's going to be a skew symmetric matrix. And then there is this V sub B vector, which is the infinitesimal vector of a translation, which is a velocity. So that makes sense, right? Okay. And then for screws and twists, okay, I gave you the intuition of screws. You can represent them in various ways. Okay, so there is an axis of the screw, and I gave you the intuition, right? That So now, essentially, why did we bother to do the screw stuff? Otherwise, we could have had rotations and translations. We wanted to get one number which corresponds to the amount of movement. So I didn't have one number correspond. I had one number corresponding to the amount of rotation, right? Rotation in and that mapped to the time variable. So I have some angular velocity and then some speed of rotation, and then for a certain amount of time, it converts to so many radians. And now, for this general displacements, I have a rotation and a translation, and these are in different units and blah, blah, blah. But once we convert this into a screw motion, then you've got one unit, right? Which is movement along the screw. And that movement along the screw is simultaneously doing a rotation and a translation. And when you do it for a finite amount of time, like 3 seconds or whatever, after that 3 seconds, you've got the rotation done, you've got the translation done, you're all really happy. Okay? So, right? Is this intuition clear? Okay. And there's a picture of a screw. And then the exponentiation mumbo jumbo works on top of this. Okay, so when you apply this exponentiation exponent of a twist, you get like a full rotation and a translation. So this works out. Now, the fancy way of, there's a fancy theory from which all this comes. This comes from so-called Lie group theory. So there's a Norwegian mathematician called Sophus Lie, who at the end of the 19th century developed this idea of groups, which are also manifolds. So a group operation does not need to be continuous, but when a group is a manifold, then you have that additional structure. And when you have both of these structures, you get what's called a Lie group. And then a Lie group, when you consider the so-called tangent space of this manifold, that gives you what's called the Lie algebra. And what we have done here is a special case of that fancy theory. Okay, I will not get into all of that. Just I'm trying to invoke authority so that you are convinced that what I'm talking about is not nonsense. Okay, and and we use this notation lowercase SE3, uppercase SE3. So uppercase SE3 is the special Euclidean group, which is rotations and translations. And then the SE, the lowercase version, is the differential version, the infinitesimal version, where the rotation part is kind of the skew symmetric matrix and so on. And you can get the equivalent of doing the Rodriguez formula. You'll get the exponential of this guy. You expand it out, you get blah, blah, blah. Okay. So I'm not going to do all that. This last slide now I need to say something, which is that, so far we were in the world of Euclid, geometry. I need to get to the world of Newton, forces and torques. Because what do your robots do? They move a point in space, the end effector in space. But what's going on inside? Inside there are motors. There are motors which are moving these joints. That humanoid you saw earlier, it has motors, electrical motors, right? They move, they rotate, okay? So what does a rotating motor give you? A torque, right? Okay, what is a torque? So essentially we know about forces. Torque is kind of the counterpart of that for angular motion. And a torque is sometimes also called a moment. And basically this is R cross F, where R is the position vector and F is the force. So R cross F is the moment. And of course, since when it's R cross F, you can imagine converting this to skew symmetric matrix multiplication, blah, blah, blah. So when we have so just like we have in the Euclidean world, we have an angular velocity and a translational velocity. So here we want to have forces and torques, or forces and moments. And so this is going to form a 6 vector again, right? Because the forces in the 3-dimensional space is a 3 vector, similarly for the torque. And this combo, the 6-dimensional combo is called a wrench. Okay. So there is a funny paper title. The paper is not funny. It's from Bernie Roth, who is one of the pioneers of this, applying all this to robotics. Which is wrenches and twists. And so the title of the paper is Screws and Wrenches That You Cannot Buy in a Hardware Store. Okay, because he was trying to teach this stuff. So anyway, so wrench is the term for the 6 vector, which corresponds to a force and a moment. Okay, and now when you take the dot product of these guys, so you take the dot product of a wrench with a twist, what are you going to get? You're going to get some work, mechanical work, right? Force dot product with a displacement gives you work. So here it's going to be the same thing. Okay, and all this stuff about, I mean, so the beauty of this whole screw space theory is that it gives you a very clean general formalism. You can talk about changing coordinate frames, and all of that comes out very nicely. Okay, so so now let's go back to our robot. Okay, so there is our robot. This is your UR2. We have UR2. We have these upstairs, by the way, on the 8th floor. And now I think all this terminology should make sense, right? So what is this? There is the S frame. There is the B frame on the end effector. The screw axes for each joint. Okay, you know because each joint is doing a rotation and a translation. So it's equivalent to some screw axis. And yeah, I mean, now if you read all the words on the slide, they should make sense to you. Okay, and then and now when you have your robot arm, the robot arm has these links, right? It starts from like, so if I consider my arm, there is a shoulder, and then there is my I think this is called the humerus, and then I have these next 2 bones, the radius and ulna. So there are some degrees of freedom at each joint, and what's happening at each joint I describe by some exponential of some screw motion. So that's what is going on here. So right, you get this, the original configuration, the base configuration M, and then this product of exponentials, right? So because there's one exponential corresponding to each joint of the robot. So suddenly this should make sense. Okay, and then now I'm not actually giving you all the details, but with this setup, the forward kinematics problem and the forward dynamics problem can be solved quite elegantly. Okay, and often, of course, for controlling a robot, we need to solve the inverse kinematics and inverse dynamics. And again, all that stuff has been worked out. So this is not an active research topic. We can do this. What's interesting is, and we will talk about this a few lectures down the road, is how does a baby learn its inverse kinematics? Because when a child is born, and a child has all this, I mean, nobody programs into their neural networks all these exponentials of screw axes, right? The child has to figure out its kinematics and inverse kinematics by its own exploration. And in fact, the child's body, unlike one of our robots, is changing over time because the child is growing. So therefore, all these bones are changing in their length. So therefore, the child has to figure out its own kinematics. It has to figure out its own inverse kinematics, and it has to manage to keep updating its solution procedures as he or she grows. And there will be a lecture, a few lectures down, which is called the developmental approach to robotics, where I'll tell you a bit about that. And of course, the mundane aspects. I mean, that's what when we have a robot has a URDF, and this is a format for specifying the geometrical and physical properties of a robot. So we use this in our various simulators. The simulator should use a URDF in the simulation environment. Okay, So I have 15 minutes, so this is great. I can get into the next part of the talk. So I won't give you a break because I already gave you a break. So I'm starting on my lecture 2B. Okay, so let's stop share. Where do I need to do something to stop share? Stop share. Okay. Okay. So now my next lecture, which I'm running behind. Okay, and then I need to start share again. Okay, and then oh, is this probably not displaying properly in the is the speaker's view? Yeah, okay. What am I gonna do here? Okay, let me stop share and start share again. Stop share. And oh, I think I have to probably unplug this guy. Let me try again. Okay, is this good now on Zoom land? Okay. No, it's not good here. It's good. Okay, everybody happy in Zoom land? Okay.
Yes.
So I'm going to talk about, okay, now, as I say, now to something totally different. So in this class, I'm going to kind of alternate between very sort of engineering robotics type stuff with very much, humans and so forth. So I want to talk about hands now. And actually, before I'm going to just end by switching to this video, but let me talk about where I'm coming from. Where I'm coming from is that we want to understand what humans use their hands for. And there are a few data sets that we have constructed in the computer vision community. So I'm going to link you to a couple of those. One is called the 100 Days of Hands. And this is a lot of video of humans doing stuff with their hands. I think you should go in there and peruse it because this gives you a flavor of what's all the variety of stuff we do with our hands. There's another data set called something something. Okay. And this is also an example of what people can do with their hands. And these are little video clips that people have collected. So what's our eventual goal? We need to have robots do all of this, right? And but first, let's understand how humans do all this. So to get to this, I want to let's see. I want to play this video, but I think it's going to complain until I have. Oh my God, I'm back to the same mess. Okay, what I want to do is I want to play a video which is on the human hand, and let me just play it a little bit so you people can see what it is, but then you can watch this yourself at home, I think. I don't think you need this from me. So I will actually kill this, okay? And okay, what we are going to do is I have a 15-minute video which I found on YouTube, which explains the anatomy of the human hand. Instead of my playing it in class, I think you guys can watch it at home, right? But what I will do instead is what I was going to do next, which was talking about some human I apologize for being not very organized about this. Okay, now where is my... Zoom window, share. Share. Then I should play, and then I should plug this in. Okay, let's see if this succeeds. Yes, okay. So this is work with Housie, who's sitting in the back row there. And we'll send you a link of this video on the human hand, which is sort of one of these anatomy lectures from people who are teaching medical doctors, right? So I was going to play that in class, but that's a waste of my time and your time. But instead, let me get to this slide deck, which is about common atomic manual actions. So what am I going for? Essentially, what is our goal? What's our research here? We want to be able to have robot hands do everything that human hands can do. That's our goal. This is what's called dexterous manipulation, right? The full dexterity of the human hands, that's what we want to achieve. And then what you see in these data sets like something or 100 days of hands is some flavor of the variety of human actions. What we find when we look at these videos is that it is overwhelming. The range of things we can do with our hands is incredible. So I'll just pick one example. I mean, I can unbutton my shirt. I can tie my shoelaces. I can thread a needle. The list of actions that humans can perform is huge. And how can we hope to get a handle on it? It's not easy. What we can do is, because actions can refer to flying, going from here to Boston. That's an action. So actions are at a hierarchy of scales, and there isn't, so it's an infinite set. It's like sentences in English, they're infinite set. So to make this tractable, we will refer to atomic actions. What do I mean by atomic actions? Actions which are on the time scale of like 1 second. Okay, there's a data set called AVA, which is atomic visual actions. So this is like AMA, atomic manual actions. Manuals refers to hands. So this is from with your hands, what actions can you perform when you're talking about a duration of 1 second, some kind of controller for that. Okay, so that's the atomic manual actions. Common, because even under this umbrella, you get lots and lots of weird cases, right? And this list will be infinite. So the hope is like something like a 90-10 rule, that I want to find a small set of actions which capture 90% of what we normally do with our hands. And we are talking about here about hands being used for object manipulation. We also use our hands for Communication. I mean, when I'm talking to you, I'm moving my hands. Gesture, right? Communicative gesture. We give people hugs, right? So hands are used for multiple purposes. But I right now only care about hands for the manipulation of objects. That's what we'll limit ourselves to. And we are going to consider atomic actions, and we'll consider common actions, because that way I can restrict the set to something tractable. And let's see what we get. So we can come up with common English verbs, right? These are common English verbs. And essentially, you can think the something data set at the same idea. You have a verb followed by an object. So insert could be, your Apple phone adapter. Insert could be one Lego brick into another Lego brick. So it's the verb insert, but then there's an object which can vary. Or you can have actions which have an object and an indirect object. So I slice an onion with a knife. Then there is a knife, which is a tool, and the onion, which is the object, right? So this is the philosophy. So basically, this is like a list of English verbs, and we are trying to see what are the actions here. And let's look at that. And Jose went and hunted out some videos. So here's an action, pouring. Okay. Now I want you to now start to think like a robotics engineer and basically ask the question of what is the degree of freedom what are the degrees of freedom that you need, and what is the sensing that you need. So when you are doing this pouring task, what do you need? You need to grasp the object. Maybe tactile matters in terms of the sense of getting a good grasp. But as you are pouring the liquid, the weight of the object changes. And you sense that. We pour, as I'm pouring from a jug. So that's a tactile haptic thing. Humans are very good with their hands. They can judge the weight of an object. Is vision needed? A little bit, because you need to direct the stream. I mean, you will find some actions where vision is kind of not really needed. It is needed to plan the action, but not actually to execute the action. Okay, so that's pouring. Stirring. This one, do you need vision? I don't think you need vision.
So almost all the tasks there can be, well, not all of them, but at least 50% of the actions can be only predicted if you know the trajectory. What's happening?
I mean, you are executing a trajectory, and I'm saying that, I mean, we all know, like I can certainly, when I'm stirring something, I can keep on a conversation and look at something else. So the vision is not necessary. Vision may be necessary to get your hand to the right place, but vision is not necessary here. Cutting with a knife. Here I would use vision, I think. Probably wise, right? Okay. But I should actually read the literature on this. Blind people, if they manage to cook their meals, that means they must find a way of managing without it, right? So because you have a good proprioceptive sense, you know where the parts of your body are. So anyway, this is, I think that this is not something we can do well with our robots today. Tool use is something which is currently quite deficient in robotics. What people do with tool use is what I regard as totally cheating, which is to use different grippers for different tasks. I would never do that, right? I mean, you should use your one set of hands and then just use a knife, use a fork, use a chopstick. I mean, as opposed to 30 different tools. And there are papers on that kind of stuff, but that to me is not the real solution to the problem. Here's another example, inserting. So inserting is kind of interesting because so in robotics, we talk about position control and force control. So position control is you want to put the object in a desired position, and then force is about forces, right? So insertion is a delicate thing because you want to put in, you care about the position, you have to insert the peg into the hole, but the forces have to be right, because if you don't, if you are slightly wrong, then you will be applying very huge force, and then either the robot or the Lego pieces will get damaged. So you want to have force in the wrong directions be 0. So it's a combination of a force and position control problem. Screw, unscrew. I think you need vision to locate the screw and to have a sense of the size of the screw and so on. And I mean, sometime later in the semester, we'll talk about a project here that Toru led, which was on untwisting objects. And vision was necessary because you need to plan and have the location of the screw. But when you are actually untwisting after that, you don't need vision. You probably need vision to initiate, but not to continue. Writing. I can certainly write blind. This is not a problem. We can all do this. But think about this from a position and force control point of view. Is there anything to observe there? What should be the force in the direction perpendicular to the whiteboard? Pretty close to 0, because otherwise you will destroy either the marker or the whiteboard. Yeah.
So isn't there an argument to say that you do need vision to keep on writing maybe and progressively more and more slanted lines?
Yeah, so so always a vision will improve the feedback, will improve the quality of your work, but it comes at a cost because vision is slow. For humans and for machines, whenever you add vision in the loop, there goes 200 milliseconds. Because it takes 200 milliseconds, like visual recognition, which is quite fast, supposedly, takes 150 milliseconds. So essentially, you're adding this delay always. And that's why I'm not such a fan of so many of the robotic solutions today, where they use vision in the loop. For very fast actions, this is not such a good idea. It's a good idea if you have a good model. So if you can be predictive, then again, this 200 milliseconds doesn't hurt you. Because you are predicting, because even though there's a 200 millisecond delay, that's only if you're starting from a blank slate. If you are running a predictor, then there isn't this 200 millisecond delay. So we need to have a prediction is necessary to cope with the 200 millisecond delay, which is kind of a feature of vision. Wiping and painting. These are, again, very good examples where force, it's a combination of force and position control, because the force you apply is in the tangential direction. In the normal direction, you want it to be 0, right? And you want to apply just a little bit of force because that's going to necessary to wipe. Hammering. Okay, this is an example of tool use. Drilling, another example of tool use. Scissors. So this is a pretty delicate operation. So think of how we pick up a scissors and use it, right? So I like scissors as an example because for decades, people in robotics thought that they had solved grasping. So there was this concept of a forced closure grasp, which enables you to pick up an object. You sort of cage the object and you pick it up. You can do that, but that will be of no use to you in terms of using the scissors. Picking up the scissors is not the point. You have to have it in the right orientation to use it. So this actually tells you that another problem we care about is reorientation in the hand, because typically you pick up an object and then you rearrange it to be in the right configuration. So reorientation goes hand in hand. Sorry for the pun, with tool use. Rolling pen. Okay, this is good. Peeling. Peeling is interesting. Most of these tasks, actually, they don't require too much vision. They require a little bit of vision. And you use vision in this predictive mode to deal with not having the 200 millisecond problem. Okay, breaking bread. Clearly, blind people can do that. Okay, so this is pull handles and draw. Rotation. So there's a famous video that you can find on YouTube, which is there was a DARPA robotics challenge some years ago where they had this Atlas robot, and then this culminates in the robot just falling off because it couldn't open a door, right? So, and I want to use this to for one of my favorite rants, which is there are people who argue that, oh, parallel jaw grippers can do everything because you can use two hands and parallel jaw grippers, and now you can do everything. The point is, yes, you can do it sometimes, but if you want a robust solution, you really do want a multi-fingered hand. And fingers, human fingers, and we'll go into this in the next lecture, human fingers are soft and compliant and full of sensors. Handing over objects. Okay, throw and catch, these are good because these require use of forces, obviously, right? Because you want to impart a certain initial velocity to the object. Catching is, by the way, a great problem for vision, because when you are suppose you are playing baseball and you are a fielder, you have to run to where the ball is rather than where the ball will be rather than where it is now. So it's a task for prediction. So prediction, you will see, is a recurring theme, and prediction deals with time delays and okay, stacking blocks. Okay, now it's getting a bit pick up utensils. Anyway, hitting with a bat. So I want to use this as an example to make the following point. Humans are very good at zero-shot learning, but then you need lots and lots of training to become really good. So I don't play tennis, but if I go to the tennis court and somebody hands me a racket and a ball, I can probably play a legal serve, right? Why? Because there's transfer from, I've hit some other objects with some other kinds of bats, and then we know something about the physics of balls and so on, and then I have a lot of visual observations of watching tennis matches and so on. But to get really good, that means that you have to get good in your own body. I mean, that can take decades, and I will never become a Federer, right? Pushing, sliding. Okay, this is an example where generalization is important. So this example is kind of bizarre because normally when you think of pushing and sliding, you think of pushing and sliding some object on a table. But this is on the floor, and it requires bimanual and all that. Pushing is an important example of what's called non-prehensile movement. So we use the term prehensile. Prehensile refers to grasping. So when you hold an object, that's prehensile movements. But is everything that we do, so parallel jaw gripper, these are all designed for prehensile movements. But is that all we do with our hands? No, when we tap on a keyboard, or when we tap on a piano, or when we push an object, these are all non-prehensile movements. And we need to pay equal attention to these and not just prehensile movements. And with that, I end. I'll let you go. Okay.